Back, everyone. So I gave you kind of a general overview, and now we're going to dig into some details. First, I'm going to say a bit more about mathematical definitions. What is an E-variable? What is an E-process? And then I'm going to explain to you this idea of thinking of what happens with E-variables and with E-processes in terms of sequential betting. And I'm going to do that with simple nulls and simple alternatives. There will be a little sideshow about a special type of E-variables. Then I'm going to talk about composite nulls and alternatives. That's kind of what you do in practice, because simple and simple is just too simple. And then I'm going to talk about something I've already alluded to informally, like what do we mean by when is an E-variable good? Like I said, like you wanted to intuitively, you wanted to grow under the alternative, but how can we formalize that? And then I'm going to talk about this idea of changing alpha after you've seen the data and why it's so important. So a little bit about random process theory, tiny little bit. So again, I have this null and alternative. And I'm going to restrict myself to the case where they define not just a distribution for one outcome or a fixed batch of outcome, but for a sequence of outcomes. And such a distribution is called a random process. So if you don't know what that is, for this talk, you can simply assume that there is some huge maximum time, maybe 1 billion observations, more than you will ever see in practice. And every distribution in your model defines a probability distribution over the whole sequence of outcomes until this maximum time. And what you see at every earlier time is just a marginal distribution. So at time 1, you see the marginal distribution of all possible continuations until n max marginalized to time 1. At time 2, you see it for the first 2, etc. Real random processes generalize this to the case where you can have infinitely many, where there's no maximum outcome. So there could be arbitrarily many. But we don't really need that here. So just think of standard probability distributions. The important thing is that there's a notion of time. And at every point in time, you have seen a certain amount of data. Time 5, you've seen the first 5 outcomes. And you just don't know what will happen in the future. So, as I said, a random process is a kind of the formal way to generalize this to arbitrarily many outcomes. But we don't really, I'm going to skip it here for the time. Now, 2 very important notions are stopping rules and stopping times. So a stopping rule is just something which tells you at every point in time a rule for stopping. So it could be like you do coin tossing and you say stop as soon as I've seen 3 ones or stop at 100. These are both valid stopping rules. And a stopping time is then a random variable which comes from a stopping rule. So if you once you have this this stopping rule, which at every point in time says either stop or continue, then at some point you do stop, and then you have this new random variable which gives you the time to stop, and that is called stopping time. So for every stopping rule, you can make a stopping time, and vice versa. So here's some examples. So stop at n is 100 is a stopping time. Stop at the first n at which you've seen 2 ones in a row. Or stop at the first n at which the standard p-value is smaller than 0.05. That would then be an invalid p-value because it assumes that you had a fixed stopping time. But as a stopping time, it's valid. It's a valid time for telling you when to stop. But you can also stop as soon as your e-value, if this is an e-value, is larger than 20. There's a problem with this one. Can anybody tell me what this problem is?
You don't necessarily know it until you...
Exactly, yeah. So this is not a stopping time. And this is actually, I said, e-hacking has already been happening, where people stopped when they had the maximum. So they track an e-process over time, maybe for 1,000 outcomes, and at 730 it had its maximum, they stopped there. But you cannot know it's the maximum when you're at 730, right? You only know that when you're at the end. So this is not a valid stopping time, just to give you some idea. Now, the formal definition of an E-variable, we define it formally for it doesn't have to be a fixed sample size. It's just some random variable which can, not always, but usually be decomposed as a vector where you stop at some point. So you have some stopping time tau, and then an e variable as superscript tau is a function of the data which goes on until you stop. So this is not necessarily a fixed length vector. It may be shorter for some data and longer for other data. So this could be like you stop as soon as you've seen 2 ones. So this would be any vector which ends in 2 ones and has zeros and ones before that. We call an e variable if the expectation of that thing is bounded by 1 and it's non-negative. So until now we looked at the case where n was fixed, right, where tau was a fixed n. And the value is called the e value. So likelihood ratios, including base factors with a simple null, are e variables irrespective of tau. That's actually something I use when I said before you can actually decompose them as a product of things. That is reflected in this. You can take any stopping time you like. If you look at the expectation of this thing under the null and you have a simple null, then you get this cancellation again. And you get 1 because the sum of all outcomes of a random variable has to be 1. So if the null is simple, then likelihood ratios, base factors are e variables for any stopping time. Now, the formal definition of an e process, and now you can see that this kind of generalizes what I did before the break, is it's a random process, so it's a function of the data. So it tells you for every sequence of data, it has a random variable which only looks at that initial sequence. So it's S1, which only looks at X1, S2, which looks at S1 and S2, S3 looks at S1, S2, S3, etc. And it has to have the property that for any stopping time, it gives you an e variable. So you can stop for whatever reason. You don't have to know what the reason is. If you have a stopping time, then the resulting thing is an e variable. Then we call it an e process. So it has the sequential nature. At time 5, it's something which looks at the first 5 data points. Note again that the base factor and the likelihood ratio have this property. For time 5, the likelihood ratio is just a function of the first 5 data points. We call this sequence of things an e process if no matter what your stopping time is, you have this expectation bounded by 1. And as I said before, this works also if the stopping time is not actually known to the analyst. Like your boss says you have to stop now, but looks at the data. Of course, if your boss can look at the future, then it's not a stopping time anymore, and then everything can go wrong. But if your boss has to look at the same data as you and for some reason decides to stop, then because we know that an e process is an e variable and all stopping times, everything works, no matter what reason the boss decides to stop for. You still have probability that it's larger than 1 over alpha is bound by alpha, so you have to type 1 error guarantee. So here's maybe one more example. So if you do a test for whether a coin is fair or not, and you get this binary data, and you see this data, then it could be that you don't know if the stopping time was stop at 6 or the stopping time was stop as soon as you've seen 2 ones. If you use an e process, it's fine. You don't need to know what was the underlying rule. You get if you stop there and you reject if alpha is smaller than if the e variable is larger than 1 over alpha, you have to type 1 error guarantee. So armed with this, we're now going to look at this betting interpretation, and I'm going to start with. You have a question? Yeah.
So does that imply you can just look at the data and say, "Oh, it's good. Let's stop now"?
Yes.
Okay.
You can. Yeah.
Thank you.
There are certain caveats for some e process, but I'm not going to. That's like that's lesson 4. I'm not going to do that here. Or actually, maybe I am. Well, we'll get back to your question later. Yeah, so I promise to you that I can interpret everything in terms of betting. And I'm first going to do that in a simple versus simple case. So now, very unrealistic, I'm going to look at, let's say we test whether a coin is fair versus whether the coin has probability of heads 3/4. And that special case of using e-values, not on that name, has actually been studied a long time ago, already in the 1950s, by Kelly, well-known economist. So it's called Kelly betting. And this is really also what happens in a casino. It's really exactly the same. So suppose I have a finite set of outcomes, and for every outcome there's a ticket. And you can buy a ticket, and it pays off a certain number, like 1 over P0, I call it here, if the outcome is K. And otherwise, you lost everything you put on a ticket. And you can buy arbitrarily many tickets, and you can also divide your money arbitrarily about them. Like, we assume money is infinitely divisible here, so there's cents, but there's also tenth of cents, etc. So think of this as indeed the casino, where you can bet on red or black, and you get twice your money. If you put money on red and the outcome is red, you get twice your money back. Why twice? Because the probability of red, if it's a real casino, real roulette wheel, is 1/2. 2 is 1 over 1/2. This is the generalization where you have some distribution over the null, that's your P0, and the kind of the fair thing to get back, where you don't expect to win or lose, is 1 over the probability. And the ticket is just putting your money on red or black. So you start with, let's say, $1. You have some starting capital. You invest it in ticket 1. And so in the ticket 1 means ticket at the first point in time. And you put a fraction of your money on outcome K. Let's say you put 30 cents on red and 70 cents on black. So that would be the P bar 1. And then your total capital gets multiplied by basically what you get back. If you put everything on 0 or on everything on, so let's say everything on red and the outcome is black, then you have like 0 divided by 1/2, it's 0. If you put everything on black and the outcome is black, then you get 2 times 1, you get 2, right? And in practice, you might put some of your money on red and some of black, and then you get what you put on, the outcome is red, you get what you put on red times 2 back. That's what you do at time 1. At time 2, you play the same game again, another draw of the roulette wheel, and you reinvest all your money. So maybe after round 1, you started with $1 and you now have $1.20. So now you put a part of 1.20 on red and another part on black. You get back what happened for the actual outcome times 2, and that's your money at time 3. And you go on like that. And then at some point you stop, and then clearly this is a multiplicative process. If you win 10 euros at some point, you can reinvest 10 euros. If you put 8 of them on red and you get red back, then you have 8 times 2 is 16, so it always multiplies. So what in the end you get back is the product of all these individual outcomes. This is actually exactly how it works in a casino. If you always reinvest everything you have and you assume that you can even invest very tiny bit amounts like cents. In the casino, you could also put your money, for example, on one number, like 13, and then actually you get back 36. If 13 actually happens, you get back 36 your outcomes, because that's 1 over the probability of 36. 1 over 1 over 36 is 36. Now the crucial thing, and here is you see the expectation is one thing for the first time again, that this game is in a real casino, you don't expect to gain money. And you can formalize it as saying that under the null, under the distribution, that if it's a real casino, the expectation of 1 over the payoff is 1, because that's just P0 divided by C0. And more generally, if you put your money on different outcomes, like a fraction here and a fraction there, it doesn't matter. The expectation stays 1, because it remains a linear combination of things with it's a weighted combination of things with expectation 1, which is expectation 1. So you always have expectation 1, which means that you're somehow doing something with e-values implicitly. And the interpretation is you don't expect to gain any money. So the idea now is this is what happens in a casino. So the real casino, you have to think of it as a null hypothesis. You're going to a casino, the null hypothesis is this is a real casino. I'm not going to make any money. The alternative hypothesis is there is some structure in what happens with this meal, and maybe I can make some money if I bet correctly. And so this P bar, so normally when you also see that this looks like likelihood ratios, right? If you can see here that at any point in time, you put part of your money on red and part of black, and that's the weights have to sum to 1, so they're like probability distributions. That's the P1 here. And you get a payoff, which is 1 over some probability distribution. So formally, your capital at every point in time is given by a likelihood ratio. It multiplies like likelihood ratios multiply, so it's kind of the same thing. But the interpretation is quite different. It's not that you think that this is some true distribution and this is another true distribution. It's more like that you think these are payoffs which would be fair under some distribution, and this is how I gamble. This is my gambling strategy. So if I think that red comes up more often than black, I can have a clever strategy for putting more money on red. I will get rich, even if I don't know exactly what is the actual probability of red. So this should never be thought of as a real distribution. It should really be thought of my strategy for trying to make money. And this is also like when we talk about good e-values, they're like clever strategies for making money under a certain whole class of alternatives. They formally have they formally look like particular distributions, but that may not be the picture you have in your head. So, well, I just said that the P1 bar is a betting strategy which determines the payoff. And obtaining evidence against the null means getting rich in a situation where you would not expect to get rich if the null were true. If you were in a real casino, you would not expect to gain any money. If you do, you have evidence that there's something funny about the casino. And this turns out to hold completely generally. So what I told you here is only for likelihood ratios, and base factors are simple null, so they're the simplest e-values, e-processes. But you can generalize this. We will see that in a moment. So now how to choose a strategy? Well, as I said, for now, let's assume a simple alternative. If you think the alternative is that red has probability 3/4, then you should actually put 3/4 on red of your money at every round. That's kind of the cleverest thing to do in some sense. Why would that be? If you're like a decision theorist, you might now protest because you said, hey, that's not true. My expected gain is the largest if I put all money on red, right? If I think red has probability 3/4, I look at what is my expected payoff, put all money on red, right? That gives you the most expected payoff. Yeah, but that's if you only play the game once. If you put all money on red, it might still be that the outcome is black, and then you've lost it all and you cannot reinvest. And that's the crucial insight here, that we never want to bet the farm, as they call it in the in the stock markets and the casinos, like put everything all on once, because then you might lose it all, and then it's game over, literally. So it turns out then that you somehow want to hedge your bets a little bit, but at the same time, of course, you could also put like 1/2 on black and 1/2 on red, and then you will always get exactly back what you invested. It's useless, right? That's like an e-value of 1. So you want to be somewhere in between. And it turns out that this, what's called proportional betting, which was actually suggested by Kelly in the 50s, is in some sense, at least in the long run, it's a strategy that makes your money, if you really think the alternative would be, you know what it would be like 3/4 versus 1/4, it makes your money grow fastest in the long run. Important takeaway is the all or nothing strategy is silly. And now we're going to make a little detour. We go back to to classical testing, where, you know, if we do simple versus simple, then one way of doing that is a likelihood ratio test, also classically in Nyman-Pearson, and then you just take P1 versus P0, and you reject if that's larger than some threshold. That's even the optimal test in classical testing, which minimizes the type 2 error. It gives the maximal power among all tests which satisfy type 1 error guarantee. So that looks very similar to what we do, right? Our test will be also a likelihood ratio, interpreted now more in terms of bets, but it is a likelihood ratio. So what's the difference? Well, we would reject the null at level alpha if this thing is larger than 1 over alpha. Whereas in Nyman-Pearson, you reject it whenever this is larger than b, where b is chosen such that the probability under the null of being large is exactly 5%. This is always more conservative than this. And actually, if you calculate b, you see that it depends on the sample size n. Our threshold does not depend on the sample size n. So you see that there's a clear difference there. This is kind of the most greedy thing you can do. And we do something less greedy. But we still use the same test statistic in simple versus simple testing. Now, what does this have to do with what I just said? This actually relates to your question also. There's also something else we could do in the e-value world. As I said, we usually use likelihood ratios, but the only thing that really matters is that we have expectation bounded by 1, or we can think of it in terms of gambling, that we bet in some way that's where under the null we cannot expect to gain any money. So what we could do is, let's say we observe a p-value, like in the z-test. Somebody else does a test and gives us a p-value. And now we say if the p-value is smaller than 0.05, small or equal, we make an e-variable of 1 over alpha. And if it's larger, we make an e-variable to be 0. So I call it the Nyman-Pearson or all or nothing e-variable. It's either 0, and that happens if the p-value is larger than alpha, or it's 1 over alpha if the p-value is smaller than alpha. This is a valid e-variable. So this is maybe a bit confusing now because I talked all the time about likelihood ratios, and now we have e-variables which are something different, but this is a very important insight. This is also okay, it's an e-variable, because its expectation is probability that p is smaller than alpha times 1 over alpha. Well, by definition of a p-value, that's alpha or smaller, so that's alpha times 1 over alpha plus 0, so its expectation is 1. So this is a valid e-variable, we could use it. And it amounts to betting the farm. It's in the e-value world, what you do here is you bet all your money. Let's say you look at a few rounds together and you make a bet where you make sure that where it happens that either you get 0 or you get 1 over alpha, nothing in between. You won't expect to get money on the null, so it's a valid e-variable, so you can do this. But it's also very funny from a betting perspective because there's a big chance that you lose it all and you cannot reinvest in future outcomes. However, if you use this e-variable, you're actually completely mimicking classical Nyman-Pearson testing because you will reject whenever the Nyman-Pearson statistician will reject the null at the same alpha. Does that make sense? We're now imitating classical testing with e-values. And this is also very important to know that our theory is not an alternative to Nyman-Pearson classical testing, it's a generalization. Classical Nyman-Pearson testing is the special case you get if you use these all or nothing e-variables. And then you think, hey, but wait, classical Nyman-Pearson testing is based on p-values, and how is that? Well, the thing is that everybody writes down p-values when they do testing, right? They write medical papers. They said, I rejected the null and my p-value was 0.029 or something. And they have all these lists of p-values. If you look at the most important book about statistical hypothesis testing by Lehmann, what he says is that statistics is decision theory. You have to make decisions with bounded probabilities of being wrong. And then he says it's useful to also provide the p-value because it gives more information, full stop. That's the only thing in this 500-page book he says about this procedure of mentioning the p-values. If you think about what we do in e-values, we say Nyman-Pearson testing is fine, we're just generalizing it. But what we do not think is fine is writing down this p-value and thinking of that as evidence against the null, because we say it doesn't have any clear interpretation. Rejecting or not has a clear interpretation, but writing down a small p-value is like, it has no interpretation in terms of accepting or rejecting. So we can do everything without the p-value, and then this is just a generalization. However, in practice, so we could use Nyman-Pearson e-variables, which are either 0 or 1 over alpha, but we don't do so in practice because they can be 0. And we don't want that because then we cannot, then we're kind of dead in terms of optional continuation. If we then get a new batch of data with a new e-value and we multiply, we stay at 0 all the time. So we want to avoid those, but in principle we can use them. And we're just generalizing the existing theory. And here, so now it's really a pity that Rianne couldn't be here, because she knows a lot more about it than I do, that in fact, in multiple testing, it's kind of even nicer because there you can show that every procedure that's admissible in some sense, so that means that there's no procedure which is always better and never worse, has to be based on e-values. For example, if you're interested in false discovery rate. But yeah, so that was really an enormous breakthrough. And here's a little bit about like, okay, what is the underlying reason? Why does it work like that? It's something I already said. Multiple testing, what's important is if you average e-values, you get an e-value, because if something has expectation bounded, two things have expectation bounded by 1, you average them, it still has expectation bounded by 1, even if there's arbitrary dependence. That's what makes them work for multiple testing. And for this optional continuation is the fact that you can multiply them, which makes it work. So it's really multiplication and addition. Both are problematic with p-values. So now let's make this a little bit more realistic. What if we have composite alternatives? So now we think maybe our casino is biased, maybe we can get rich, but we don't know how. Like maybe red is more often there than black, or maybe black more than red, we don't know. So we somehow now want to learn this. How can we do this? So one thing to do is to use a distribution that somehow better and better mimics the truth by trying to learn it. So, and here's a classical way of doing that. At time t, if you've seen n1 reds and n things in total, then the next time you put a fraction of your money on red, which is n1 over n. That's kind of the maximum likelihood based on the past. Well, that's actually not a good idea. Okay, does somebody know why it would not be a good idea to do this? To put, you've seen like, yeah? Exactly. This risk betting the farm again. Yeah. If you've seen 3 reds, that's even quite likely if the distribution is like 1/2, 1/2. Next time might be black, you've lost it all. But if you change this a little bit, by adding a little bit here and a little bit here, you smoothen it slightly, then it turns out that's enough to not have this risk and to very quickly get rich. Let's say if it's like 3/4 in reality, the probability of red, or 1/4, then this will very quickly converge to the right to 3/4 or 1/4, which will make you rich exponentially fast. So this is a clever strategy to use if you don't know the alternative. It's some probability not equal to 1/2, but you don't know what it is. Yeah, I think this is what I need to say about this. Yeah, so if you now think about this again, you see that, okay, so now you kind of adaptively reassigned your money at each point in time based on what you saw in the past. Yeah, one thing that's important is that even though now you're learning things and your alternative changes, this does not affect your type 1 error guarantee. The probability that this thing will ever get large is still small, independently of whether your current estimate of the true probability is good or not, right? Because the expectation bounded by 1 still holds. Now, once you start doing this, you can kind of start thinking in reverse. Okay, every time I have some probability of the next outcome given the past, so I can multiply all of these, and that defines somehow a distribution for all sequences. It defines kind of by reconstructing a marginal distribution over all sequences of every length. Right? Normally, if you have a marginal distribution, you can write if it's a multiplication, gives you a sequence of conditional distributions. Here we do the opposite. We start with the conditional distributions, they're just our strategy, and we reconstruct a marginal distribution, which I denote by a bar, which is this thing. Now the question is, what is this marginal distribution? Well, we will see in a moment what it is. Let's first look at a different way of doing this. So one thing we could also do is, well, we've seen base factors with simple null e-values. We have a simple null here, which is like fair coin toss, Bernoulli 1/2. So we could also get an e-process by taking a base factor, and that would look like this. And so one interpretation of this is that it's just we have all the different alternatives and we average over them. So if basically many e-processes running at the same time, it's like somebody who's gambling at the casino with probability of red 3/4, somebody with 4/5, somebody with 5/6, and we average over all of them. That's kind of what's written here. It's an average over many e-variables. But you can also think of this, because this is a marginal distribution, as a product of conditional distributions. That's always possible, right? Every marginal distribution. Previously I said I have a sequence of conditional distributions. I can look at what is the marginal distribution. Now I have a marginal. I can look at what is the corresponding sequence of conditional distributions. So it's the product of the one is always the same as the probability of the other. Now if I compare these two, see that if I take the Bernoulli model with a uniform prior, so I just put the uniform density between 0 and 1 and take the integral, then this probability distribution of the next thing being a 1 given the past is actually the same formula I've just seen. Actually, it was already derived by Laplace around 1800. He used it to calculate the probability that the sun goes up tomorrow. It's an interesting story. But so this is actually a very old formula. And what this means is that we have basically two very different ways of looking at the same thing. We can say we're going to learn the alternative by making an estimate of the past and using that in each round. We look at the past to make an estimate and using that for the next outcome. Or we take an average, a base factor, and we look at the average e-value, which is a new e-value, and they both give the same results. One thing you think of it as averaging, and the other thing you think of as sequential prediction, where you learn from the past. And it gives you the same result. And this just gives you an idea like why something like this you could expect to hold more generally. If you look at these base predictive distributions, so these are as a Bayesian, you would, for the alternative, use a base factor. The marginal decomposes as these predictive distributions. You can rewrite them as the average probability of the next outcome given the past, but you averaged according to the posterior instead of the prior. And because the posterior will go more and more concentrate on things close to the MLE, the maximum likelihood estimator, you will actually, your Bayesian sequential predictions will look more and more like what you would get if you would just take the MLE from the past and use that for prediction. So in general, you can always do both, and they're not always the same. So that's also an important thing to keep in mind. So in the Bernoulli model, these two things are really exactly the same. If you take a uniform prior, you get the Laplace rule of succession. If you take a smoothed maximum likelihood estimator of the past, you get the Laplace rule of succession. But in general, taking a plug-in estimator of the past and taking a base predictive distribution for some prior is similar but not the same. And this plug-in idea is actually often called frequential plug-in. It's invented by Phil David, famous statistician. So here, for example, if you would do this with our normal running example, if you would do there actually it's okay to do the plug-in estimate, just the MLE of the past, because probability densities will never get 0 anyway for normals, different than from Bernoulli. If you would do that, or even if you would add something to smoothen it a little bit, just like in the Laplace rule of succession, you get again this, basically this is the MLE of the past, and here you add something to smoothen it a little bit. If you would take the Bayesian e-variable, where you take a base marginal likelihood in the numerator, if you decompose it as a product of e-variables, then the individual things in that product will be normal densities, but they will have a larger variance than the variance you started with. So here it's kind of not exactly the same, but it's still very similar. Like you could either directly, and what we do in practice when we work with e-values, we do just whatever is more convenient, because we're not married to a Bayesian approach, but we do like it. So if we can get something that's easy to calculate with a prior, we use that. If it's easier to just use an estimate based on the past and then multiply the e-variables for every estimate, we do that. So now I'm going to go to composite nulls. Maybe again this is a point for asking questions. Okay, I'll just go on then. So this is kind of going to take quite a while. So I'm first going to go back to how to construct these e-processes in a sequential way. And then I'm going to go back to our bounded mean example, which you've seen before the break. That was a big example with a composite null, where we just said we want to test whether the mean of a distribution is 0, but we didn't assume that it was normal or could be discrete, continuous, whatever. We just assumed that it had a bounded support. Well, implicitly you've seen this before, but now I'm going to make it more precise. So we talked about these past conditional e-variables, which were things with this property. At sample size n, they look at the first n data points. So they're again a random process, right? You can look at M1, M2, M3, M4, and the nth thing is a function of the first n data points. It's always non-negative, and the expectation is bounded by 1. And then if we multiply these, this is in the literature, in the probability literature. If you multiply things like that, you call it a test supermartingale. You don't really have to remember that word here. I'm just saying it for the few people who may have heard of this before. Now I define an e-process as something where your expected, its expectation is, it also was a random process, and now you added an arbitrary stopping time, and its expectation was bounded by 1, no matter what stopping time you used, right? That's how we define an e-process. And it turns out that if you have these sequential past conditional e-variables, things with expectation bounded by 1 given the past, and you multiply them, you get an e-process. Historically, it was known that you get a test martingale, and that a test martingale is something where you have expectation bounded by 1 no matter what the stopping rule is, so you could do optional stopping. Then 6 years ago, they found that this is actually, the notion of e-process is substantially more general. So there are objects which have expectation bounded by 1 on their, so they are random processes, they're sequences of things. You can stop at any time you like, they have expectation bounded by 1. But you cannot easily write them as a product of things that, as a product of things with expectation bounded by 1. For us, we will only look at things which were historically called supermartingales. So all the e-processes we're going to look at are of the form, you have an e-variable for the ith outcome given the past, for every I, you multiply them, and then you get your e-process. Which we already did right in the beginning when we did optional continuation. We basically had an e-variable for every kind of batch of data, and we multiplied them, and then we created our e-process. Then we had an e-value for every individual outcome. In the bounded means example, we multiplied them, we had an e-process, and all our e-processes look like that. So now we go back to this testing the mean of a bounded random variable. So we don't assume anything, we just, our null is distribution of these outcomes is IID under some distribution with mean mu, and we don't assume anything at all about it otherwise. Discrete, continuous, a mix, could be anything. So again, we set our e-variables for an individual outcome as 1 plus lambda times x minus the mean. So this must be an e-variable because its expectation is 1. Notice that again we have to make sure that we choose lambda in such a way that the e-variable is always larger than 0. Otherwise it's not an e-variable anymore. So now if we multiply this for fixed lambda, we get an e-process. That's the construction we've just seen. So expectation always bound by 1. You multiply, then the expectation of what you get under any stopping time turns out to be also bound by 1. And now the question I asked before the break is like, how should we now find lambda? Well, now we know. We can basically, at every point in time, we can look at the past. We can look at what lambda would have been good to use in the past. What does good mean? Good means large. Because you have an e-variable, so you know under the null it's not going to be large, but you want it, if the null is not true, you want it to be as large as possible, so you can reject the null, so your confidence intervals become narrow. So at every point in time, you pick the lambda, which would have given you the largest e-variable, the largest e-process so far, if you had picked that all the time. You're allowed to do that because it's past data, right? Your lambda does not depend on, if you would pick the lambda which is best for your current data point, your expectation would not be bound by 1 anymore, because then lambda would be part of the data, and then this thing here, lambda would depend on x, and this would be larger than 1. But if it depends on the past, it's fine. So at every point in time, you look at what lambda would have been the best. You plug in that lambda. It's a plug-in estimate. And then you start multiplying these things over time. And this is a bit like maximum likelihood. But now we don't have a likelihood, but an e-process. So e-process is really, again, it doesn't look like a likelihood anymore. It's a product of 1 plus lambda things. Very different from a likelihood. But we use it in the same way. We think about it the same way. Maybe some of you might know, I know at least one of you knows about partial and conditional likelihoods in the literature. They've always been kind of a bit fuzzy concept. What exactly is that? Well, you can kind of put all of them, they are all e-processes. So this really unifies a lot of generalizations of likelihood from the past, where things like maximizing it based on past data and so on make sense. So now we go back to betting. Now we see this is a little bit different now, because we don't have this clear, in the casino we had finite number of outcomes, and we had this payoff which was 1 over the probability that would be the right probability under the null. We don't have that anymore, but we can abstract away from it. We can say now you get basically a general bet. What is a general bet? Well, it's a random variable which has expectation 1 under the null, which means you can. So now you don't buy a ticket. So in the casino example, you could divide your money in different ways. Now you actually start by a single bet where already something has been decided for you, like it has already been decided that there is maybe 2/3 goes on red and 1/3 on black. And that thing has expectation 1. So you can buy that thing wholesale. And then you get the payoff that corresponds to that. And if the expectation is bound by 1, that means that if you do this, you don't expect to gain any money again. And if it's larger than 1, you again have evidence against the null. So it becomes a more abstract game now, where at every point in time, you can buy something for €1, where you expect that you get back, if it happens, to get €1 or less back. And then you decide what to buy. So in the bounded mean example, for every lambda, you have this ticket where you get back, you pay 1, and you get back 1 plus lambda times x minus the mean under the 0. You expect to get back exactly what you put in. So it's a fair bet under the null. And if you get more, you're lucky, and you get evidence against the null. And what you do as you go on is just like in the casino game, we started learning what was the frequency of red in the past to inform our bets, to make more clever bets in the future to make more money. Here we can look at what lambda would have given us a big win in the past, and we're going to take that lambda in the future. And this is now completely general. This idea of like there's abstract bets where you put in money, you expect to get back that amount of money or less. If you get more money, that's nice, and you always reinvest and you multiply. That's kind of the general story. Okay, so we are now at 45 minutes. I don't know if I should do maybe a quick toilet break. If people are... yes? Okay, let's do a 3-minute break. Go ahead. 5-minute break, perhaps. Yeah, sure, you can ask questions in between.
What is the relation between these and other testing procedures, like using bootstrap or permutation tests?
Bootstrap is, I don't know, it's quite different, so it's hard to say.
Yeah.
Permutation tests can be actually kind of rephrased in this. Yeah, I would need some time to but there are several papers about evalues and permutation. So basically, you take standard permutation tests, you change them a little bit, you get an e-value test.
So
But I would...
also generalize permutation.
Yes. But yeah, exactly, it's the same thing. You can make them like all or nothing tests, and then they are just like the standard permutation tests. Or you can make them kind of have different values, and then they generalize it. Yeah, I don't have it on the top of my head how to do it, but this is actually quite a big topic. Yeah, Bootstrap, I really don't know.
Yeah, in your previous example with like the lambda that you can like, in the example with the lambda that you can optimally choose the lambda. I know that like in this case lambda was bounded, but like if lambda wasn't bounded, it would still be like a valid e-value, and then
It would still work, yeah.
But couldn't you just like arbitrarily choose large lambda to reject like any number?
No. That would if you would do that here. Yeah, that's actually interesting. What would happen? So, so here lambda had to be bounded, otherwise you could get negative e-values, and then the whole thing crashes anyway. So, if you're in cases where lambda could be unbounded, there's a variation of this with unbounded outcomes. But to make sure it works for unbounded outcomes, you actually need to add a penalty for to get this expectation bounded by one constraint right. You can show that because they're still not allowed to get negative, you need, so the way they work is they do something like, they look like something like this. You must add something like this to get the expectation bound by one constraint in order. And this will again make sure that, so you have to pick pairs of lambdas and gammas for which this is non-negative, and then magically this cannot happen. It's somehow kind of in the formulation make sure that this will never happen. But I mean, again, I would have to think a bit about the details, but.
So e-values cannot be, like, they're strictly non-negative, right?
Yeah, that's, it's kind of, because this gambling game kind of, that would amount to a game where you can borrow money. And it actually, I guess it might make sense. You could kind of try to generalize the theory to that, but then everything would change. That's,
Thank you.
So my question is on choosing lambda based on the pseudo max likelihood. Is that a heuristic, or is there some sort of guarantee that this is the best construction of lambda you can have?
Ooh, that's a good question. It's a heuristic. It's not bad, but there are better things you can do.
And perhaps more of a tangential question.
So it's actually what is really the best thing to do is an open question. But if you, again, it's all depends on how you define good and best. But one thing that kind of the most funky thing that people have done is to you can basically transform the results from the Bernoulli case to this case. Even though if you have Bernoulli 0 and 1, you say that, okay, now I assume that the outcome is not on the corners, just 0 and 1, but it could be anything in between. And then you can show that there's like these are some of the most important results in this theory, that strategies which are good for the corners are also good for being in between somehow, because the corners are the worst case. So if you get sequences with only zeros and ones, they're kind of the hardest sequences to deal with, in the case where you can have real valued outcomes as well, as long as they're bounded between 0 and 1. So then what people did was just take this Laplace strategy, actually not the Laplace strategy, but there's also called if you don't do +1 divided by +2, but +1/2 divided by +1, that's what you get if you would use Jeffreys prior in Bayesian statistics. And in information theory, it's called Krzyzewski-Trofimov. That thing has, for Bernoulli, some optimality properties. And now what they do is they just transfer that to the bounded case. So they say that, okay, I get a Bernoulli, I get like a probability of 1. I could look at what lambda is that if I would assume that I'm in this bounded mean case with continuous outcomes, and all my sequences would just happen to be zeros and ones. There's like one choice of this lambda which would give you exactly the same gain as this Bernoulli thing, and that's the one you take. So okay, I guess this is way too complex to, but so it's a very funky idea, and it works very well in practice. And you can also prove things about it, that it somehow has some, so there's many, this is one of the things people have tried.
And my other question is, in the case of testing a mean of a bounded process or random variable, how does using the e-value, say, compare to maybe using something like Hoeffding's inequality to
it's much better. There's a
sense of the
paper, so this
tightness
paper
of the
by
bound?
Woodby, Smith and Ramdas is, so that it was compared to both classical ways with using Hoeffding and Bernstein, and then there's the empirical Bernstein, all these variations. That's one thing you could do, or you could do non-parametric base. That would be another thing, and it really is much better than both of them.
better in what sense?
In the sense that, so that's the optimality I want to talk about. I will explain, but really again, if the null is wrong, it grows faster. So and if you make confidence intervals out of it, which you can do with both the Hoeffding and with this, they are significantly narrower. So the paper is full of, it's very hard to prove this actually, but that is like that this works better than Hoeffding. But they just tried it. They tried Hoeffding confidence intervals, and they made anytime valid confidence intervals with this lambda hat approach, and they showed that they're just a lot narrower on many problems.
Would this be something that could be applied to, let's say, like a bandit problem?
Yeah, I think that has actually even been done. I mean, I would have to check, but I think it has. Yeah. This can definitely be applied to bandit problems. Yeah. Okay, let's continue. Some other examples. So now I'm going to look at kind of simpler cases, if you will. We have parametric nulls again. So let's say the t-test, for example. So one sample t-test, we want to test whether the mean of a normal is 0, or confidence interval for means of normals. But now we don't know the variance. So the null could be mean 0 with any variance. We just don't know what it is. So one thing you could do is, that's very crude. So we know that this is not an e-variable anymore, right? We've seen that. That's because we want to have this expectation bounded for every distribution in the null, but this will only be bound if we take expectation under this marginal. But what we could do instead is kind of divide by the MLE. Like we take the maximum likelihood in the null. This will always be bigger than this, right? Because here you take an average over theta, and here you take the maximum theta, and you divide by it, so it gets smaller. And here you can show that the expectation of this thing is the expectation under some unknown theta, any distribution in null, of this divided by the MLE. And because the probability density of the data under the MLE will be larger than under the true theta, or definitely not smaller, this expectation will actually be bounded by 1 for every theta in the null. This has been called universal inference. it's very crude. So in practice, I don't advise you to use it, but that's why it's called universal. You can always do this. But it's in a way, it's kind of almost cheating. It's like you make the null as bad as possible for you, and then you always get expectation bounded by 1. And so in practice, it's usually not competitive, but for some very complicated problems, this is the only thing we know how to do. But we can often do more clever things. Well, here I actually even gave the derivation that, you see this must always be smaller than this. This is the Emmeline, so, and that's 1. So now if we do this for the t-test, again, so this is our null. Sigma squared is unknown, these are alternative. So we set this and we divide by this, and you have an e-process, but it's not a very good one. It will typically not get very large if the alternative is true, which is what we want. So for the t-test, we can do something better. And this may seem like magic now, but in a moment we will see like general ways of coming up with things like this. So what we can do is, let's take for the alternative first a given effect size, which they often do, for example, in medical testing. So the effect size is a scaled mean. It's the mean divided by sigma, so it's kind of scale-free. So you assume the effect size is some delta. The null is again any normal with arbitrary sigma, and the alternative is any normal with this effect size. And now what we're going to do is we're going to take our data points and we're going to pre-process them in a sequential way, so that we never need to know the future for pre-processing. So we divide basically everything by the first data point absolute. Why would you do that? Well, the first data point now becomes either 1 or minus 1, right? Because there's nothing else. You lose kind of this information. You only have 1 bit for your first data point instead of the whole data point. And the second one becomes something weird. It's like this ratio and then this ratio. Now, the cool thing is that all these things now are scale-free in the sense that if you would measure your outcomes in kilograms or pounds, normally the data would be different, but now it's not. Now it's the same because the unit of measurement has disappeared here if you divide everything by the same data point. And this is very nice because this means that actually the distributions of these ratios do not depend on the variance anymore. So if the null is true, these x's have mean with some variance, and the distribution depends on the variance, but these things have some distribution. It turns out to be a t distribution, which does not depend on the variance anymore. So now we have a simple null. And because we have a simple null, we can now use likelihood ratios again. So, and that's actually what people have done for the t-test. You just change your data like this, and then you take these likelihood ratios, and it gives you an e-process. So it sounds like a trick at this point, but you'll see that it comes from something more deep. Yeah?
So the way you choose your first observation will change?
Well, your first observation, you get it, right? You observe data.
Okay.
Yeah.
It's assuming that you know the order, right? So if you get a batch, you cannot do this.
Yeah, that's true. Wait, what's happening? I guess I'm out of electricity. Just a moment. That's because I'm used to. Normally when you put a Mac on a screen, it gets automatic electricity, but not here. Wait, can I? Is there? Oh, he just went away. I'm afraid that if I unplug this, I'm causing a problem. Oh, he is getting a cable, maybe. Ah, okay. He anticipated it. Can I just put it in, or will the screen? That one you can put maybe on that one, yeah. could have thought of that. Let's see if this might. Yes, great. Well, another little break. Yes, so now if you don't know this effect size in advance, you can again put a prior on it, just like a Bayesian would, because now we have a simple null again. We put a prior on the alternative, we can do everything. So this is another example. So now I'm going to kind of show a general way of making such e-variables for parametric nulls. And also I will finally, I said it already many times, like what do we mean by optimal, by a good e-variable? So now it's going to get a bit technical, but bear with me, because it's also going to be really interesting, I think. In fact, this is kind of how we got into it. This was our breakthrough in these 2019 papers. So I first need to define something. So I already told you in the beginning, and that's what I'm going to formalize now, that there is this general theorem. If you give me a prior on the alternative, I'm going to make a corresponding prior on the null for you, such that the corresponding likelihood ratio base factor will be an e-variable after all. I'm going to explain how to do that. So I have this prior on the alternative. I have my base marginal distribution, which is the thing you see there on the top. And now let's look at the prior on the null. We have a composite null, like the t-test, which minimizes the KL divergence to the alternative for the base marginal distribution. So among all these priors you could take, you take the one which makes the KL divergence smaller. This is called the reverse information projection of the base marginal on the, essentially the convex hull of the null. On the set of, basically the set of distributions in the null, which you can, it's bigger than the null itself. It's what you can get by taking mixtures over the null, base marginals. What you can see here, this is basically what you project to. Of course, it's not Euclidean, so take this with a grain of salt, because nulls are usually not convex in statistics. So you just take the closest among all priors. It's called reverse information projection because we project on the second argument of the KL. I don't know why that's then called reverse, but the standard information projection is projection on the first argument. And it's not symmetric, so therefore you get something different if you do that. So this is our claim to fame. It was our 2019 papers and made it to GRSSB in 2024. If this prior exists, then the resulting base factor is an e-variable. So its expectation is bound by 1 for every distribution in a null. Not going to prove it here, but the idea of the proof is basically, well, if you know Bayesian statistics, they're often like worst case priors that have some minimax properties, and this is kind of a similar flavor. In a way, it's a minimax convex analysis argument, which shows that such a prior exists. And in fact, this is not just any e-variable, and now we're going to talk about optimality. It's the GROW e-variable, and by GROW we mean growth rate optimal. And by definition, that's the e-variable which maximizes among all e-variables you have for the null, the expected logarithm on the alternative. So notice, so we are Bayesian about the alternative here. We say the alternative could come from some base marginal distribution with some prior W1. And we want among all e-variables, and definition of e-variable only talks about the null, we want the well that has the maximum expected log under the alternative. Now, why the logarithm? So First of all, an e-variable by definition, the idea is expectation bounded by 1 under the null. It doesn't grow under the null. Under the alternative, we want it to grow, so we can reject the null as fast as possible. So you would like to have an e-variable which maximizes expectation of some increasing function of s. But then the question is, why would you take the logarithm? Why not just s itself, or s squared, or square root of s? Well, this is again something which goes back to Kelly, a name we've seen before. It's called the Kelly criterion, and why would you want to do it? Well, the short answer is that everyone does it, because you get nice math. But let's see if I more precisely. So there are some very good reasons for doing it. If you maximize just the expectation of s itself, or square root of s, or s squared, then the solution, the optimal e-variable, under that criterion, will be an e-variable which has probability 0 under both the null and alternative for some value. So it can So it can be 0 with non-zero probability. So you can have an event which has non-zero probability, which makes it 0, and this means that you cannot do this optional continuation thing anymore. Well, you can do it, but you can start betting the farm. So a very crude way of justifying the logarithm says that we never want to do that. So we want to have some increasing function which makes sure that the utility for putting 0 on some outcomes with positive probability is minus infinity. So we'll always avoid doing that. And the logarithm does that for you. This is, of course, a crude way of explaining it, but it's one way. There's a better way, which says that, well, if you look at what happens if you get a lot of data, let's say we do this again on the batch. We get studies, different studies, and we're going to multiply the e-values. So multiplying e-values means adding the logarithms. And because we add things, we can work with the law of large numbers. And the law of large numbers tells us that the average of the sum, so the normalized sum, the average, will go to its expectation. Right? So if we take, for every batch, we take an e-variable, and we look at what is the average of the log in the long run, it will go to the expectation. And this means that at least if you have a simple alternative, so not a prior but a simple, so one distribution on the alternative, that if I take at every point in time a certain e-variable, it makes a lot of sense to take the one which, if I would take one for which the logarithm is always epsilon smaller, then I would converge to something epsilon smaller here on average, which means that the actual value of my e-variable would be e to the minus n times epsilon factor smaller. So it would be exponentially smaller than what I get if I take the one which optimizes the logarithm. Right? So optimizing for the logarithm basically means optimizing for under the alternative, you want your e-value to grow exponentially, and you want the exponent in this exponential growth to be maximal. And that's what you get if you optimize for the logarithm. I said a while ago, like in this casino game, we want to do proportional betting. If you think the probability of red is 3/4, we want to put 3/4 on red. Not everything, because then we might bet the farm. And this 3/4 is exactly what you get if you optimize for the logarithm. So it maximizes your growth in the long run because of the law of large numbers. And it's very nice, but in practice, actually, this also has problems, because it really, if you do experiments with this, so this is what people nowadays do in practice, and this is what you get if you use this special prior, which I told you about, gives you this. So this is kind of mathematically also convenient. The problem with this in practice is that if you do experiments with this, you see that if you compare this to any other method for making e-variables, which maximizes maybe not the logarithm but something else, then in the long run, this really beats them completely. But often you're already happy if your e-variable gets larger than 20. And that's not the long run, right? You don't need a lot of data before you can see, like, hey, I can reject all these hypotheses. And in the short run, this thing may not always be very good. So nowadays we have all these papers on kind of having e variables which still cannot be zero, but which, on the other hand, kind of trade in the long rate growth for they're a bit worse in the long term and a bit better in the short term. And you can use Renyi instead of KL divergence for that, but that's kind of really beyond. And this is also very new. So until like a year ago, everybody used this grow e variable. So the theorem says I get, this is the e variable I get if I take the special prior. It's among all e variables the best one in this expected logarithm sense. On the alternative, the logarithm grows as fast as possible, and that means that the exponential growth is as fast as possible. This was our claim to fame, but interestingly, it has last year been extended enormously by in a paper by Martin Larsen, who's a real mathematician, different from me. He knows everything about measure theory and things like that. And so they show that this basically works under you don't need any conditions. Like you can generalize this even to the case where these priors are sometimes not achieved. So you take the minimum, you take this information projection, and so you can find priors which make the scale divergence smaller and smaller, but in the limit there is no prior, but then they show there's still something else. There's still some e variable you can have, which is kind of the limit, even though the limiting prior doesn't exist anymore. And it becomes very general. It's basically, this is you give me any distribution on the alternative and any null, and I give you this growth optimal e variable. It doesn't have any irregularity conditions at all, which is really surprising. Now, what do you know? What do you do if you don't know the if you don't know? We said, okay, here we are still basing on the alternative. What if we cannot really formulate a good prior on the alternative? Well, then you can do a joint information projection, it turns out. So now you have alternative and null, and you can put priors on both of them, and now you take the two priors which minimize this projection, where the null and the alternative clearly have a different role, because KL divergence is not symmetric. And this is called the grow with a W. Was not such a good name because you pronounce it like grow without W. Growth optimal and worst case e variable, which minimizes the worst case growth. And that's something we can do if we don't really know a good prior on the alternative. So that's the minimum over all distributions of the alternative of the maximum over all e variables of the expected log growth. Here's a simple example. Let's say you have a monotone likelihood ratio family. So all exponential, one-dimensional exponential families are that, or also the if you're in the t-test setting, so the distribution of the t-statistic has this monotone property. So there are many classical families, not complicated families, but classical families which have this property. Then if you have two distributions, a null and an alternative, about the same parameter, but the null says it's smaller than delta 0 and the alternative says larger than delta 1. So think about the normal mean example. The null says smaller than 0 and the alternative says larger than 1.5. Then if you do this joint information projection, you actually get 2 point priors, which put all their mass on the two closest points, on delta 1 and delta 0. So it's very intuitive, right? This is kind of intuitively the worst case situation, when your null is as close as possible to the alternative and vice versa. And that's what this joint information projection will do in this very simple case. So you get degenerate priors, which would probability 1 in the alternative on delta 1 and 1 on delta 0. So in the end, it's just a likelihood ratio. Another thing which goes slightly beyond the theorem as I showed it to you. So you have a generalization of the theorem where this also fits, is again the t-test. So now we said our null is all normal distributions with mean 0, and alternative is unknown, and the alternative is all normal distributions with mu over sigma given by fixed delta. Delta is 1, say. Otherwise, we don't know. And now what is the optimal e variable? Well, how do Bayesians do this? Well, Jeffreys, the famous Bayesian, said in this case we should use a Bayes factor, of course, he's a Bayesian, with right Haar prior, so-called right Haar prior on sigma, which is given by 1 over sigma. That's weird because that's not a real prior. If you integrate it over 0 to infinity, you get infinity. But Jeffreys was a physicist, so he was not bothered by stuff like that. And he instead said, and I think that's, I mean, mathematicians sometimes laugh about it, but he said like, well, usually the only prior information we have in such a case is that we want our inferences to be scale-free. If we measure in kilograms or pounds, it shouldn't matter for the outcome because that's arbitrary. So we want a prior such that we get a procedure which gives the same outcome irrespective of our unit of measurement. And then he showed that there's only one prior which does it, which is 1 over sigma. So that's really like how physicists think. I really like that very much. So he says that that's kind of the only reasonable choice. Now the miracle is that this is the same thing I showed to you where I said divide all data points by the first data point and use a likelihood ratio test. It's the same. So you can put this 1 over sigma prior on W. Our theorem, actually, you can apply it to this, and it tells you it's the optimal E variable, and it turns out to be exactly equal to this earlier E variable I gave to you. So that's really nice. We have this old idea by Jeffreys, used by many Bayesians. Actually, some of them don't like it at all because they say the 1 over sigma prior makes no sense, but it's kind of vindicated with a completely different interpretation now, because you can also think of it as an E variable, which works no matter what distribution in null is true. And it's even so the growth optimal E variable. Well, I should say one more thing. I see that there's a slide missing here now. So a caveat here is that in general it doesn't come out so nicely. So you can use this grow construction. It's for any setting. You give me a prior on the alternative. I make a prior on the null, and we have this in this likelihood ratio. Base factor gives you an E variable. We also did it for 2x2 tables. It's another classical very simple classical problem, and there we get something nice. It works very well in practice, but it's not at all equal to anything that has ever been done in Bayesian statistics. So there you get there you get something. There's also Jeffreys prior for that problem, but we get something completely different from Jeffreys prior if we want to make this E variable. So it's really problem dependent what you get. Okay, so then the last thing. I hope you can still. You must be tired and hungry. So I hope you can bear with me a little while more, 15 more minutes. And that's this thing. That's the final thing. That's the other big selling point of E variables. So there's this thing with statistics that practitioners generally don't understand this idea that you need to fix alpha beforehand, and they find it very counterintuitive that if you set alpha 0.05 and then you get a p-value of 0.01, you cannot say that, okay, my alpha was 0.01. And I think also that statisticians give them a very bad idea because they say, well, write down your p-value. But then the question is, what does this p-value mean? If like, you have alpha 0.05, and I say, yeah, but my p-value was 0.01. You have more information, but you have more evidence, but how much? How can you can you quantify this, measure this? Does it have any repercussions for making decisions? There's nothing in traditional theory which tells you that if you have a smaller p-value, you can do more. So with e-values, we can do something. But it's not as simple as you might think. We cannot just say our type 1 error probability can be changed if we have a smaller. If we have a large e-value, we have a smaller type 1 error probability, because the type 1 error probability is still defined before you see the data. It's not a conditional notion. So there's something else going on. So here's a motivating example. So let's say we have some new bad disease, so a treatment for a bad disease, which was tested at the 0.05 level 10 years ago, but it gave a super small p-value, so it was very impressive. Everybody who got treatment X was cured, and nobody who didn't get it was cured. So there was special approval given, but then they never produced the drug because it was far too expensive. But yeah, it really works very well. So with the small p-values, so people kept thinking like maybe we can make it cheaper, right? And after 10 years, Kelly discovers a new production process, and now it's suddenly much cheaper to make this medication. Now, maybe if you would have a 5% error probability, this would still be too risky to now make a factory where you produce the medication. But if it would have really been 0.0025, which is where the p-value was at, it might be worth the risk. Of course, this is very idealized. In practice, you also want to know something about how big is the effect and so on. But this is just like to give you an idea. What is definitely true is that if you see an impressive result, then based on that result, you might start thinking about, hey, maybe we have to change the whole problem. And if we change the problem, then maybe what was first too expensive now becomes a rational thing to do. But it's not clear. You know that the small p-value means something, but you don't know what. You cannot use it as alpha, so you cannot make any calculation about what is the expected losses and gains if you build this factory. So is there some way to use the p to make a rational decision? Another example where we actually kind of cheated in the real world was the COVID vaccinations. When the idea, at least in the Netherlands, people all talked about, we're going to have these vaccinations. Probably they're going to work with more than 30% of the people we vaccinate, and then we should probably give them to the elderly. That was in the first year of the COVID outbreak. So there was really talk about give it to the elderly. And then they had the Pfizer data, and it was not 30%, it was 95%. Like almost everybody who got the vaccination got cured very fast, which nobody had expected, not even Pfizer. So then people suddenly started talking about maybe we should vaccinate everybody over 40, or maybe even the whole population, which is a lot more expensive, there's a lot more danger of side effects, but if it works really that well, it might still be the rational thing to do. And the important thing is that there again, the data changed the problem, right? Because the data was different from the way they expected it, they started thinking about the problem in different ways and different actions, building more expensive factories, vaccinating everyone. With p-values, you can't really do that. People did it anyway with COVID, which was a very good idea probably, but there's no math you can do about this. And this is, of course, a well-known problem. It's been called the problem of roving alpha. Like, either two ways of thinking about it. I have a very small p-value. Can I take more drastic decisions? Or I have a very small p-value, can I adjust alpha? It amounts to the same thing. Now, people, of course, have an intuition about this. So sometimes they think, well, if I get very small p-value, then maybe among those studies in which I have a very small p-value, I make a type 1 error much less than in the overall setting. Well, this is just plain wrong. That's the problem where if everybody tells me, yeah, I find p-values like they tell me evidence against the null, I find them intuitive, then I'm really a radical guy. I say like, what does it mean? Because this is not what it means. Because if indeed you're in a world where the null is usually true, some subfields of psychology have that problem, it's almost always true, they're called null fields. Every now and then you will see a p-value smaller than 1 in 100 times. Given that you see a p-value that's smaller than 1 in 100, the probability that you make a type 1 error is still 1, not 0.01. Because you always make a type 1 error if you reject. So this cannot be it. So we need to do something else. Well, then, of course, you can use e-values. They have an interpretation if you change alpha after seeing a lot. So you see a large e-value, say this is a lot of evidence, so I make my, my alpha different. However, under a different interpretation of alpha, not under error probability, but a different interpretation. And so in the last few minutes, I'm going to give you that interpretation of alpha. For p-value, it still doesn't work, but for e-values, it works. So it's actually a very old interpretation. It goes back to 1939. One of the most influential papers in the history of statistics. It was actually the paper where minimax estimation was also introduced. Walt said, well, we can think of this whole Nyman-Pearson theory, which was 5 years old back then, in a different way, in a more in terms of losses and risks rather than error probability. So he said, let's say you have two decisions, accept the null or reject the null. You have two states of nature, null is true, alternative is true, and the loss you make if you make a decision is given by some function L. So you say the loss if the true state of the nature is the null hypothesis, L0, and you say 0 is 0, and the loss if the true state is 1 and you say 1 is also 0. So if you make the right decision, your loss is 0. If you make a type 1 error, your loss is a type 1 loss. True state of the nature is 0, but you say 1, and opposite there's a type 2 loss. So now you fix some bound, usually take it to be 1, but you can scale everything to any different bound. And you say, like, among all decision procedures for accepting, rejecting that I want to work with, I just want to make sure that my expected loss is always bounded by L, small l, let's say 1. So I want to make sure that for every distribution in a null, the expectation of the loss for my decision rule delta, so delta takes the data and maps it to reject or accept, 1 or 0, is always bounded by L. That is what I first was the type 1 error guarantee. That should be smaller than alpha. Here we say my expected loss, type 1 loss, saying rejected should be accept, should be smaller than L. And among those, I want things which are good in the type 2 sense. So if you get your evidence in terms of a p-value, then one way of achieving this is rejecting the null if the p-value times the loss is bounded by L. So if you take L as 1, and you take your loss, let's say 20, so your type 1 loss is 20. If you say I reject the null, even if it's true, that counts for 20 loss. Maybe that's the cost of making a factory for a medication that doesn't work. Then your decision rule is saying, like, I reject if my p-value times my loss is smaller than 1 is the same. So that's that achieves this bound, then your expected loss is always smaller than 1. So that's kind of the good thing to do here. So this, in this interpretation, a type 1 error significance level of alpha translates 0.05 translates into a type 1 loss of 20, 1 over alpha. Right? The smaller alpha, the larger the loss. It's 1 over. But otherwise, you basically do the same thing. Right? You look at the p-value. If the p-value is times the loss is smaller than 1, so that's the p-value smaller than 1 over the loss, smaller than alpha, you reject. You think of 1 over alpha as the loss you make if you make a wrong decision. But now let's assume that this loss becomes data dependent, because that's what happened in this COVID example and in this medication X example. Right? You look at the loss, and you see if the data is, you look at the data, and if the data is super convincing, you may want to build a more expensive factory, so then the type 1 loss becomes larger because the data was more convincing. Now, if you try this, like I reject if the p-value times the loss is smaller than 1 approach, now it goes wrong. Because let's say that if, for example, your loss could either be 20 or 100. If it's 20, then you would reject if the p-value is smaller than 0.05. If it's 100, you reject if it's smaller than 0.01. But if it's sometimes 20 and sometimes 100, and this depends on the data, then it could be that that in some cases you're told it's 20, in some cases you're told it's 100, it's because some policymaker decides that. And because of this choice by the policymaker, which is data dependent, your expected risk bound might not hold anymore. It might be larger than 1 or than 1. So you may now violate the type 1 risk bound. So for example, if you have a really evil adversary, policymaker, which tells you if your p-value was smaller than 0.01, the cost of rejecting, we're going to build a factory or something, is going to be 100. And if it's between 0.05 and 0.01, it's going to be 20. Then if you look at what is your expected loss with this decision rule, following the p-value, it would be with probability 0.01, you have lost 100. So that's already 1. But then with probability 0.04, everything between 0.05 and 0.01, you get loss 20 because you also reject, but with loss 20. So you get 0.04 times 20, so you get 1.8. But your promise was 1, right? Your promise here was I want to have an expected loss, a risk bounded by 1. That's what I promised the policymaker, but it doesn't hold anymore with p-values. And now it turns out that if you use e-values here, it still works. You still have this expected bound of 1. Even so, what you do now is you pick, you reject a null if 1 over the e-value times the loss is bounded by your maximum risk bound you have, so usually 1. 1 over the e-value times loss is bounded by 1. And then you will get an expected risk bound of 1, no matter what weird adversary determines what loss functions you need to deal with as a function of the data. So maybe I had another Yeah, so I should tell you that you could actually generalize this even if there's more than two. If like it's not just 20 or 100, but the loss could be any real number. And you have an adversary which the more convincing your outcome is, the bigger the loss will be, then you can even get expected loss infinity if you follow the e-value, the p-value rather than the e-value. Well, given the time, maybe I should skip the formalization. Just tell you that, so we say a decision rule is type 1 risk safe. So now we have a loss function with a subscript b. And the b determines what the actual loss is, and it can depend on the data. What we want is that the expectation of the loss, where you maximize b over all choices of the loss function inside the expectation, so then you get the worst case b, which depends on the data, is bounded by L. And then there's a theorem. So if we use this rule, you get to see a loss function indexed by b, and then you take the largest action such that 1 over the e variable you observe for the data times the loss you make with that action for the data-dependent loss function is bounded by 1. If you do that, then you get type 1 risk safe. You always have expected risk bounded by 1, and that's actually an if and only if. This is a way to characterize e-values. Basically, the only procedures which can do this for you are e-value-based procedure, where you look at the loss you actually told. Like, this is the loss for your data. Some policymaker who looked at the data told you the loss. And you reject if 1 over your e-value times the loss is bounded, then the maximum you're willing to have as a risk. You get the risk bound, and every procedure which gets the risk bound can be implemented in this way. And this means that if you don't think about error probabilities but about risk bounds, with e-values you can get this and have the risk, the losses depend on the data, which I think is what in reality usually happens. Right? In reality, the data informs the way we think about the problem, our decisions. To some extent, with these, if you think about losses, which I think is very natural, rather than probabilities, you can do it with e-values. So that was it. E-values give you a notion of evidence which is more robust, like you can do optional stopping, but you can also think of it as being more flexible. You can change the stopping time, you can change alpha, and it still makes sense. You get confidence intervals, which are also more robust. Then, of course, there is a price, and the price you pay is that in some cases you will need more data. You have to be more conservative to get this going. But there in this price, it really depends very much on how you measure the costs of doing this. Because if you look at expected stopping times, sometimes actually you might need less instead of more. But if you look at worst case stopping times, you definitely need more. So it's a complicated story, like is it really better or worse? That's in terms of how many data points you need. That's just difficult. I gave you some very simple examples, and the main future challenge also, I think, for the e-variable world is to, so we have this general recipe. If you give me a problem and I make an e-variable for you, which is even optimal in this log sense. But if you try to do that in practice, you have to do this information projection. Right? You have to project a prior onto a big set. And in many cases, we don't have fast procedures for doing that. So basically, the only cases we can solve is where it has an analytic solution. And in practice, we often have to do numerical optimization, and it gets very slow. So there's still a lot of work for the coming years. Thank you. Yeah.
Please take the mic.
Very practical question. This is quite experimental, I suppose. Is there like any chance that this becomes reasonably used by actual practitioners in like the next, I don't know, decades?
That really depends on who you ask. It's tricky. So I think it actually, what it really depends on is the field. So in tech companies, they're actually, Netflix is using this, for example, quite intensively even. Adyen, the payment company, is starting to use this. At the same time, Booking here in Amsterdam, they're not using it, and I don't really understand why not. So I do think they're here to stay. They're going to get a niche, and in this niche they're staying. In the medical world, it's much more tricky because of basically what I said, this worst case phenomenon. In the worst case, you need more data.
Yeah.
And their whole way in which they organize things is based on like planning a sample size, and then you have to plan for the worst case, and so it's difficult to get in there. And then of course there's also everybody there is busy. There's this big skepticism of new methods, always difficult. There are regulations, people are busy to learn about them, and the irony is that people are always talking about the big companies as being holding back things and so on. But here it's more like it's not the big money, it's just the big people, organization. Like they all do things in a certain way, and now we come and say, you should do it in a different way. And it's very tricky, I found out.
And you can't just click a button in SPSS, right? It's
okay, I didn't
too
talk about
complex.
it. We do have software.
Okay.
We should have made it in a way that you can just click a button. We didn't want to do that because I always thought it was very dangerous that you just click a button and get a p-value.
Yes.
So I didn't want to have a button where you just get an e-value.
Yeah.
Yeah, that was maybe not a good choice.
I don't know.
But there is software. Yeah, I can tell you more.